W-band radar architecture. The 94 GHz radar consists of three major parts: a transceiver, power board, and processing board. The transceiver generates the waveform, converts the signal to a radio frequency, RF, and radiates the signal. The power board provides power to the transceiver. The processing board samples the beat signal and transmits the data. A functional diagram of the modules is presented in Functional diagram of developed radar. As shown in, the transceiver consists of three parts: an antenna, front-end module, and phase-locked loop, Pll board. The antenna is a gold-plated brass horn antenna with linear polarization. It has 25 dB gain at 94 GHz frequency, and an approximately 10-degree half-power beam width. The antenna is connected to the front-end module with a rectangular waveguide interface. The front-end module consists of a voltage-controlled oscillator, VCO, power amplifier, frequency multiplier, bypass mixer, and multi-stage low-noise amplifier. Its output center frequency is 94 GHz with a sweep bandwidth of 1.4 GHz, which is adequate for providing a resolution up to 0.12 meters. The RF output power is 1.5 to 2 milliwatts. Its receiver low-noise amplifier, LNA, gain can be selected from 23 to 46 decibels. To synchronize the front-end module with the processing board, a Pll board is used. The Pll board synchronizes the oscillation from the front-end module with the processing board's clock. It also provides the voltage sweep required to sweep the VCO output frequency. Functional diagram of a transceiver. The processing board utilizes the Xilinx 7000 chip for analog to digital conversion, ADC, synchronization with the Pll board, triggering the Pll board, and data transmission. The chip is divided into two parts: programmable logic, PL, and a processor, PS. Its functional diagram is presented in. The processing board's main tasks are to provide the trigger and clock for the PLL, sample the beat signal from the transceiver, and send the raw data via TCP/IP. The beat signal from the front-end module is sampled by an analog to digital converter inside the PL at a sampling rate of 940 kHz. When the PL receives the radar command from the PS, the latter writes the sampled data to the shared memory. The PS then reads the sampled data from the shared memory and transmits the raw data via TCP/IP. Functional diagram of the processing board. Shows the Fmcw radar block diagram. Shows the radar module, processing board, power board, PLL, front-end module, and antenna. Flow diagram of Fmcw radar. Developed 94 GHz radar, A, radar module, B, FPGA signal processing board, C, PLL and power board, and D, front-end module and antenna. The power board consists of 4 power converters and 4 regulators. It was designed to provide the transceiver with the required power for each module. After providing the transceiver with its appropriate voltage level, the power consumption of the radar is approximately 10 W. An Fmcw is a signal whose frequency is continuously modulated. The transmitted signal can be represented by, where F0 is the carrier frequency and K is the chirp rate. The echo signal is mixed with the transmitted signal from the received signal. The received signal from a single target can be represented as, where phi is the constant phase. The received signal for a single target is sinusoidal and its frequency depends on the target range. The transmitted signal of the Fmcw radar is modulated with respect to time, and the received signal from the impulse target is a beat frequency, FB, which is the difference between the transmit frequency and the received frequency. The beat frequency is proportional to the range of the target and is represented as, the Fmcw radar repeatedly and continuously transmits the waveform given in 1. The waveform is classified into sawtooth and triangular waveforms according to the repeated form. The time it requires to sweep the frequency is called the ramp time, TR. Then, the bandwidth of the Fmcw is defined as. The radar used in the experiment was Fmcw radar with a center frequency of 94 GHz. The radar transmitted the linear frequency modulation, LFM, signal through the antenna, and it sampled the echo signal mixed with the transmitted signal. The chirp of the LFM signal used was an up-ramp sawtooth waveform. The chirp rate, K, was 1400 MHz/ms and the ramp, sweep, time was 1 ms. The sampling rate was 940 kHz. The bandwidth was 1.4 GHz, and the signal could be sampled 940 times in a single period. According to 3, the range can be represented by the function of the beat frequency as the received signal is converted to a range profile by inverse fast Fourier transform, IFFT. The range profile of a single target is obtained using 3, which is shown as where the window, WTR, serves only to take one period of the signal, and sinc x is a normalized sinc function. In the case of sawtooth Fmcw, the beat frequency is obtained by performing the FFT on the range profile. Taking the displacement on both sides of 5 gives 7. The range resolution is determined by a sinc function of the range profile, where Ts is the sampling interval, 1.06s, and n is the number of samples in an echo, 940. The beat frequency resolution is 1.49 MHz. The theoretical properties of the point-target response for Fmcw radar is a 1.4 GHz bandwidth or a resolution of approximately 0.093 meters. If the bandwidth increases, a profile with a high range resolution can be obtained. The Fmcw radar does not require a sampling rate above the bandwidth to avoid degrading resolution. The range resolution depends on zero padding. However, according to the Fourier transform properties, NTS is equal to 1/f. The range cell thus had a spacing of 0.15 meters. Therefore, 8,912 samples were used for FFT after padding 7,912 zeros. The range cell spacing after zero padding was 0.015 meters. The range cell spacing after zero padding was sufficiently smaller than the range resolution. There is no minimum range limit in Fmcw radar. However, the maximum range is limited by two parameters. For one, the maximum range is limited by the sampling rate. This is because the beat frequency is determined by the Nyquist frequency, which is equal to half the sampling rate. Another criterion is the range ambiguity. For Fmcw, when the delay time becomes half of the ramp time, the resolution doubles. Depending on the conditions, this value may vary, however, in 9-10% was chosen. Usually, in Fmcw radar, the ramp time is adequately long and the target signal exists only within the radar range of interest. Thus, the maximum range is determined by the sampling rate. Because the sampling rate is high, the distance information of farther targets can be obtained if the beat frequency resolution increases. The maximum range criterions are sufficiently longer than the length of the chamber. Therefore, aliasing will not occur. The maximum range of Fmcw radar is 15,000 meters for the ambiguous range and 477 meters for the Nyquist criterion. The chamber subjected to the experiment had a length of approximately 7 meters. The radar performance was analyzed using a trihedral corner reflector target. The experimental settings are shown in. The target and the radar were placed inside an anechoic chamber with a target distance of 2.8 meters. Experiment settings for the impulse target. As shown in, the radar samples the echo signal multiplied by the transmitted signal. The sampled signal is the deramp signal of the echo, where the frequency components are sampled. Therefore, when conducting an inverse Fourier transformation, IFT, the symmetric value of the time or range domain can be obtained. Because only the in-phase component can be obtained, only the real number or in-phase components of 2 can be obtained as the received data. Through the Hilbert transformation, a quadratic component, imaginary part, can be generated. The Hilbert transformation is a method for generating a signal that has the same magnitude but is orthogonal to the original signal. As shown in 10, the Hilbert transformation is used to obtain an in-phase/quadratic, IQ, signal. When performing the IFT with this method, the phase information can be obtained, and the symmetrical information, which can be generated as a mistaken IFT, can be prevented. The experimental results from a point target are shown in. Theoretically calculated side lobe level, resolution and experimental results are almost identical. Point target response in the range direction. The side lobe level, null-to-null resolution, and 3 dB resolution of the impulse target were analyzed. The measured resolution of the Fmcw radar, as shown in, is expressed in Table 1, which describes the resolution in the range direction. It can be observed that the theoretical resolution of 0.09 meters and the measured resolution, 3 dB, are very close. Measured resolution of the range direction.